Temperature dependence of resistivity. In this subtopic, we are going to discuss about the temperature dependence of resistivity. Here is a graph of resistivity versus temperature, and we can see the variation in the resistivity of conductors, superconductors, semiconductors, and insulators. We see here that the resistivity shows us a different behavior for all these different types of materials. Now we see here that in case of conductors, as the temperature increases, it shows us an increase in the resistivity. Whereas in case of semiconductors, it shows us exactly opposite behavior. The resistivity of semiconductors decreases with the increase in temperature. Whereas in case of insulators, we see that there is no much difference in the resistivity of an insulator with the variation in the temperature. In superconductors, we know that superconductors show us zero resistivity at a particular temperature, and as the temperature increases, it is showing us an increase in the resistivity. Now in this particular subtopic, we are going to focus more on the resistivity variation of a conductor, semiconductor, and an insulator. Now we can see here an energy band diagram that can help us to understand better how there is variation in the resistivity with the change in the temperature. So we have a valence band and a conduction band. Now in insulators, we see that the valence band and conduction band are far apart. There is a big band gap between the two bands. In case of semiconductors, we see that there is a small band gap between the valence band and the conduction band. Whereas in case of conductors, we see that the valence band and the conduction band are both overlapping. Now valence band has the free electrons available for conduction. So what exactly happens here when we change the temperature? So as we increase the temperature, let us first discuss in case of conductors. As we increase the temperature, we see that the resistivity increases. Here there is an example of copper, manganese and nickel. These are all conductors. They all show us an increase in the resistivity with temperature. So what exactly happens here? In conductors, as we increase the temperature, there are already free electrons that are available in the conduction band because the valence band and the conduction band here overlap. So when we increase the temperature, we are exciting more free electrons from the valence band to the conduction band. So what happens here is when we excite those electrons, there will be collisions between the electrons in the conduction band as they try to drift to contribute to current. So as a result of those collisions, because of the crowding of the free electrons, the conductivity decreases, and as a result of that, the resistivity increases. Okay? Whereas in case of semiconductors, we see that there are a very few electrons that are there in the conduction band due to thermal excitation. And these semiconductors, they also behave like insulators when the temperature is 0 Kelvin. So what happens here is as we increase the temperature, we are exciting the electrons from the valence band to the conduction band. They overcome the energy band gap here. And as we are exciting those electrons to the conduction band, they contribute to current. So since there is less crowding of free electrons already available in the conduction band, There are very less collisions taking place here. So majority of the electrons that are excited from the valence band to the conduction band contribute to the conductivity. So the conductivity increases as we increase the temperature, whereas the resistivity decreases. So we see here that semiconductors show us exactly opposite behavior compared to that of conductors. In case of insulators, there is a large energy gap between the conduction band and the valence band. Therefore, insulators show conductivity at very high temperatures. Then what is the equation that relates the resistivity with temperature? So we have the equation here. Rho is a resistivity at any given temperature where we want to find. Rho naught is a resistivity at a reference temperature, what we already know. In the bracket we have 1 plus alpha. Now alpha here is the temperature coefficient of resistivity into the difference of the two temperatures, that is the temperature at which we are finding the resistivity, and T naught is the reference temperature. So we see here that depending on whether it is a conductor, semiconductor or insulator, the values of alpha are either positive or negative. For conductors, alpha takes positive values. So what happens here is we know that the resistivity increases with the increase in temperature. So as the temperature increases, the resistivity here has to increase. So the resistivity at a higher temperature compared to the reference temperature will be 1 plus of quantity here. So since it is positive, it also verifies that the resistivity increases. In case of semiconductors, alpha takes negative values. So the resistivity at any reference temperature or resistivity at the temperature where we want to obtain will be less than the resistivity at a lower temperature. So it shows us that the resistivity decreases with increase in temperature. Now T naught here, as we mentioned earlier, is the reference temperature, usually taken as 0 degrees Celsius or 20 degrees Celsius, provided the temperature range is not high. So the difference in this temperature, that range has to be well maintained to use this equation. Now in alloys like nichrome, manganese and constantan, they show us very weak dependence of resistivity with temperature. And as a result of that, or due to that advantage, they are widely used in wire bound standard resistors. So in the laboratory, we come across uh, alloys like nichrome, manganese and constantan that are used as in wire bound resistors.